Today we have Bram Leenders talking to us about how we scale user privacy here at Spotify. We hope you enjoy the talk, and let's welcome Bram to the stage.
Hi, and welcome to the Stack Bytes talk discussing the design of one of the core services at Spotify, called Padlock. Padlock is one of the systems at Spotify that helps us respect our users' privacy. And the goal of Padlock is to enforce the removal of data related to our users when these users either opt out or leave our service. And we do this with a technique that we call crypto shredding. I will discuss later what that means. First, let's take a step back and get some intuition for the scale at which Spotify operates. We have a fairly large backend that processes a lot of data from a lot of users. Specifically, at the time where I'm giving this presentation, we have over 230 million monthly active users. And together, these users generate over 1 million queries per second to our backend. And some of these queries are fairly simple, and they might hit only 1 or 2 services, and some of these queries are pretty difficult, and they might fan out to maybe 10 or more services. And in total, we have over 1,000 microservices, and we have well over 1,000 batch data jobs. And we use this data in many features. For example, playlists, or generating Discover Weeklies, your weekly recommendations of interesting tracks. And we also use it for features that may not be visible to our users, like royalty calculations. And these features are typically owned by autonomous teams. We organize in feature teams, where a single team owns a feature and gets the freedom and responsibility to decide which frameworks or databases they want to use to implement this feature. And as a result, this team is responsible for maintaining this feature on their own. The problem we see here a bit is that privacy is not a feature that can be owned by a single team. Instead, privacy is something that takes an entire company to work together and all be respectful of our users' privacy. And to help our developers do this, we built Padlock as a way of centralizing the control over personal data. And like I said, we do this with a technique called crypto shredding. And the first step in crypto shredding is that you agree that you will always encrypt all data that corresponds to a user storing it. And specifically, you would encrypt this data with a key that is unique to every user. So with over 230 million users, this means that we also have over 230 million keys that we use to encrypt the data belonging to these users. And all these keys you would manage in a single central place. In our case, this is Padlock. And this means that if someone wants to access the data that has been encrypted, they need access to both the encrypted data as well as to the key belonging to the user whose data was encrypted. And that means that if we remove the key from this central place where we store all keys, then the data that was encrypted with those keys has become inaccessible. And this means that if a user asks us to stop processing or storing their data, all we need to do is remove the key belonging to that user in one place. We don't need to worry about contacting every system that might store the data. We only remove one key in one place. And in the example I just gave, I said we would use one key per user. But of course, you can tweak this a little bit and you can define your own strategies, because the deletion granularity follows from how you organize your keys. So instead of having a single key per user, you could also define several categories, and then give each user a key for every category. And then you can delete at a granularity of per user per category. And in fact, if you go to Spotify's privacy page, you will see that we have defined several categories. And if you would rather enforce some kind of retention over time, you could also, for example, generate daily keys and combine the daily keys with user keys. And then you would, for example, only store the last 365 daily keys. And that way you can ensure that data that has been stored for more than a year has become inaccessible because you throw away the key that it was encrypted with. And since you combined this with per user keys, you also still have the granularity to remove data as soon as a user opts out. And these are only 3 examples. I guess you can come up with many more depending on what use case you have. But this is just as an idea in case you want to do this yourself. So with that being said, let's dig in a little bit into how we architected Padlock. So like I said, Padlock is the place where we store all these keys belonging to all these users. And Padlock is part of the request path for many services that you might use. For example, payments, logins, using playlists, or using Spotify Connect. So when we started designing Padlock, we defined a few objectives, which have later become our SLOs. And the first of these is that we want Padlock to be very highly available. Because Padlock is part of many of the request path of many of the features that we have, if Padlock is unavailable, that means you can't use the features that it powers. So we defined that we want at least 99.99% uptime. And this is just to make sure that we're not a limiting factor in the uptime or availability of features that you like. Also, we want Padlock to be a very fast responding service. And this is because you're already used to many of the features like playlists, and we later on added Padlock into this request flow. And of course, we don't want to slow down the features that you already like, so we set a fairly tight latency requirement where we want to be able to answer at least 99% of the queries going to Padlock in at most 10 milliseconds. And also, of course, because Padlock is in the request path for so many high-volume services, we also want Padlock to be able to handle at least 500,000 requests per second per region. And we divided the world into roughly 3 regions. One is in the US, one is in Europe, and one is in Asia. And because a single region might fail, we can redirect the traffic from one region to the other. So we want regions to be able to handle not only their regular production traffic, but also the production traffic of one of their neighboring regions. And when we made some quick back-of-the-envelope calculations, we said we want at least 500,000 queries per second. Now, if you choose to implement a system like Padlock yourself, one of the first questions that you might ask yourself is what API you want to expose to your clients. And when I say clients here, I still mean backend services, because from Padlock's perspective, a service like playlist or payments is still a client. And you have 2 main options that you could get in exposing an API. One is that your clients give you a user ID, and you return a key or a set of keys corresponding to this user. And then you leave it up to the service to use these keys to encrypt or decrypt data. The other option you have is that clients will send you a plain text or a ciphertext with a user ID, and you do the encryption or decryption logic on their behalf, and you send them back the result. And these have different benefits, so it depends a bit on your use case which you might choose. In the first case, where you hand out the keys, you have very predictable network traffic, because user IDs and keys have a known fixed length, and that means that for a given number of requests per second, your traffic will be very predictable. Also, this would allow clients to do caching for maybe a second up to a minute on their own, and this can greatly reduce the load on your system. On the other hand, if you choose to do the encryption and decryption logic on behalf of your clients, you get a much stronger confidentiality of keys. Because the keys never leave your system, you don't have to worry about vulnerabilities in any of your clients. Another benefit you get is that your clients can be much thinner because they don't need to contain the encryption or decryption logic. And this can be nice, for example, if you need to support many platforms, like many programming languages. And it's also nice because it gives you a bit more control over, for example, which cryptographic algorithms are used. And maybe if you want to make any changes to that, it becomes a lot easier because you only need to update it in a single place in the service you own. So with that said, I won't go into exactly which choice we made, But let's dig a little bit into a high-level architecture of Padlock. So the smiley face on the right-hand side here represents a backend service, for example, Playlist. And when Playlist wants to decrypt data belonging to a user, they would send a request to Padlock. And this is where you already see the first thing where we valued high reliability, and that is that we decided to mirror the entire installation of Padlock, and Playlist will not know whether it goes to the regular Padlock version or to the mirrored version. And we do this because even though we use canaries and testing environments, sometimes you might make a change that inadvertently brings down an entire installation. You might click a wrong button or roll out a wrong Puppet change, and sometimes you might just nuke an entire installation. So we try to make it really difficult to accidentally destroy both at the same time. For the database that stores all the keys, we chose Cassandra, because this has been a very popular database at Spotify, and it's fairly easy to run this as a highly reliable system if you want to use it as a key value store. And to make sure that we don't unnecessarily pipe all our traffic through a Cassandra cluster and improve our latencies a bit, we also cache using memcached. And of course, since we have two completely separate installations, that also means that we have two separate memcached clusters. And I'll quickly go over some of the optimizations that we made here to make sure that we can serve traffic at this volume. The first thing is regarding our memcached setup. We've seen two main strategies at Spotify for deploying memcached. One is deploying memcached on every machine that also runs your application. And this might be known as a sidecar model if you use Docker. And the other would be having a completely separate memcached cluster, where you might even use different physical nodes for storing your memcached and your application cluster. And for this case, we preferred having completely separate clusters, because we noticed that it's nice to have a very static memcached cluster, because this means that your cache doesn't get invalidated a lot. And we see that if, for example, we choose to redirect traffic from one region or another, then we might have to scale up the number of application nodes that we have. And it's very nice to not at the same time invalidate your cache, which is what would happen if you run a cache on each of your application nodes. Because then, as you get a big traffic spike, you also suddenly get a lot of application nodes with an empty cache. And we wanted to avoid this. Now, to further make sure that if you make any small changes to your memcached cluster, like in a 10-node cluster, add a single node, to make sure that you don't invalidate too much of your cache, we use consistent hashing, which makes sure that only a small portion of your data will change which memcached node it's stored on. And we also found that memcached really helps with small reliability issues. For example, if your Cassandra cluster has a tiny hiccup, maybe there is a garbage collect going on, or maybe you had some small network issues, then it's very nice to have a memcached cluster that might have a 99% hit rate, because that means that you can still serve 99% of your traffic, so most people won't notice that you have tiny database issues going on in the back. And this is really nice for small downtimes, maybe like a second or maybe even 30 seconds. And we use an open source memcached client. So if this sounds interesting to you and you want to check it out, then by all means, you can visit github.com/spotify/folsom, and you can check it out there. The other thing I wanted to discuss is our Cassandra setup. And I should add a warning here at the start, and that is that we were using a pretty old Cassandra version. So not all the problems that we experienced may be in the newer Cassandra versions that you might download today. Also, we have a very specific use case. So if your use case is different, please verify that these optimizations actually work for you before applying them. So the first thing we do is we have a system that or a technique that we call escalating consistency. And this is where you try your reads always with a local one read. And a local one read is the fastest read you typically get in Cassandra, and it's where your application contacts a single data node in Cassandra and tries to read data from there. The problem is that sometimes there might be some replication lag, and not every data node might have data corresponding to this key yet. And this is where typically in Cassandra you would use a higher consistency level. And since we expect our services to only request users that exist, if we ever do a read to a Cassandra node and we get back a not found, we'll just retry it, but with a higher consistency level. We might start with a local one, and if we then get a not found, we can retry with a local quorum, or maybe even a quorum. And this means that for a few edge cases, we might go up to a quorum, and we still get that strong consistency. But for most cases, we'll get a local one, and we'll get really good performance. Another optimization we did was disabling the read repair. Read repair is where if you do a read in Cassandra, your Cassandra node can reach out to other nodes in Cassandra that it knows will store your data, and then it compares if all nodes have the same data. And this is really nice if there might be discrepancies between your nodes, because it will repair your cluster. But since our data changes very infrequently, and read repair can be a fairly expensive process, we only want to use explicit repairs, because this makes it a lot more predictable for us why a query might be slow. We also disabled row caching. Row caching is an optimization in Cassandra where if you read a key several times, Cassandra will keep it in memory so that subsequent reads will be faster. However, we run a memcached cluster in front of our Cassandra cluster. So if we read a user multiple times, we expect this user to be present in our memcached cluster, so we don't expect to read the same user multiple times. So storing this user in our Cassandra cluster in memory would be a bit of a waste of memory. So instead, we only use the Linux page cache, because this is where Linux will try to store an entire SS table, an entire file or a chunk of it, in memory. And this means that if we request one user and Linux decides to put this file in a page cache, the next user who might be in the same SS table will also be faster. And we feel this is a better use of our memory. We also disabled retries anywhere we could, because we feel it's better to fail fast rather than answer slow. And if our clients feel that a query is important, they're free to do the retry. But we just want to make sure that we answer fast and correct, or throw an error. We also chose a schema that tries to avoid using tombstones. Tombstones is where Cassandra will mark data as deleted. But we've seen issues in older Cassandra versions where some cluster operations, like scaling up or down or making snapshots, sometimes conflicts with the use of tombstones and can have really hard to debug issues. So we opted to avoid using any tombstones, and we explicitly override any rows with null values if we want it to be gone. Going back to our architecture overview, we recently made a fairly big change, and that is that we switched Cassandra, and we're now using Spanner. This is because we moved to Google Cloud, so we now have the option to use Spanner. And using Spanner, we get a few advantages that we couldn't have before. One of them is that Spanner scales very fast and very easily. In fact, it's so fast that we added alerting on the CPU usage in our Spanner cluster. And if it exceeds a certain threshold, we will page the on-call engineer, but we will also automatically scale up our Spanner cluster. So you have a script running that constantly monitors it, and it might double our installation size if it notices any potential problems. And this makes sure that if it's a Sunday night and I'm asleep and I get paged, and it might take me 20 minutes to find out where my laptop is and log in, our script may have already scaled up our Spanner cluster, and it might have alleviated most of the problems before I'm even logged in. It's also very nice to no longer be on call for synchronization between regions, because network issues can be difficult to debug as an engineer, so it's nice not to have to worry about any of that anymore. We also get a stronger permission model that integrates nice with the rest of the products that we're using. And as a cherry on the cake, we also get really good integration with data flow. And this is nice because we use data flow in many of our batch processing. And this is good if we want to, for example, take snapshots or backups. All right, it's the last slide already. This talk was inspired by an earlier blog about Padlock. And after this blog, we got a lot of questions around the cryptography that's used inside Padlock. So I just wanted to say a few words about that. The first thing, and the main thing really, is that our cryptography is really boring and standard. So you shouldn't ask too many questions about it. It's a very standardized algorithm using very well-known open source libraries. We didn't try to invent anything ourselves, and neither should you. What we do that is a bit special is that we use an envelope around our encrypted data to store some metadata. And this is just to make using encrypted data a bit easier for our developers. So in this envelope, we store, of course, a version of the envelope in case we ever want to change the format. We also store a list of the key IDs that were used. And this is nice if, for example, you rotate keys a couple of times and a single user might have 10 or 20 or more keys. Then it's nice not to have to try each of those keys if you want to decrypt, but instead you can immediately pick the one that was used. Of course, we also store the ciphertext, because without that there would be no point in storing anything. And we store a checksum. And this checksum helps a lot if you might, for example, do an incorrect join, or if you might request data, or if you might request keys from the wrong user. Because this ensures that if you try to decrypt my playlist with my friend's keys, that you will get a very clear error that says, this is not the user belonging to this data. And actually, using envelopes in this way is also not a super novel idea. Or at least there is an open source implementation that does pretty much the same thing. And that is Tink. It's made by Google. So if you want to check that out, it's on github.com/google/Tink. And if you use their version, you also get some nice integration, for example, with BigQuery. All right, so I promised that the last slide was the last slide, but this is the very last slide. So thank you for listening to this TechBytes talk. And I hope you got some idea of the thought that went into designing Padlock. Thank you.